Okay, first of all, thank you for joining. Thanks for being here. Finally, I will be the only one presenting because, well, my colleagues cannot join finally. Well, I don't know most of you because, well, I just joined the project a couple of months ago, but hopefully we will meet in Milan next week. I will try to give you some details on the landslides and terrain movements, which I think is the most unknown phenomenon of this project. And then I will try to give you a summary of what are our ideas together with the CTTC to assess the hazard and the emergencies of this kind of phenomenon. And well, if you have questions, you can always interrupt me, or we can do it in the end if you want. So first of all, I would like to start with this picture, which is for me a thought of why we should worry about the terrain movements. This is a picture of a valley in Switzerland, and I think it's a good example of why we are more in contact to this type of hazards, because the societies are, during the last decades, we have been increasing our presence in some areas where there was not before. So we are more in contact, we are developing our societies and our infrastructures in these areas. So we are more exposed, and we really have to care about how to live with them. Then going to this question, which is land stable? Well, obviously the answer is no, because otherwise we wouldn't be here. Well, normally I would say that land is stable, but in some cases it's not. And I would like to show you some examples of unstable lands. First of all, this is an example of a sinkhole provoked by a karst, which means that some layers of the terrain below the surface were dissolved due to the type of materials. And this is something that can cause damage in the infrastructures, as you can see in the picture, or into the buildings that are in the area. Another example is something similar, but the triggering factor is different. In this case, it's because in this surface below there were some expansive materials, which means that, well, specifically these are clays, which when they are in contact to water, they can increase the volume because the minerals have this capacity of expansivity. And this is something dangerous for the foundations of the buildings and the infrastructures. Another example, and probably the most impressive one in this case, this is a landslide that was affecting a highway in Taiwan. And this is a massive land movement that, well, the trigger for this case can be very different, but mainly it can be related to the presence of water in the soil or earthquakes that at the end they change the internal stresses of the land and they provoke a movement of the terrain. And this is something dangerous, not only for the foundations of buildings and the infrastructures, but also for people which are in a certain moment crossing this highway. So at the end, the key point of the danger or the hazard, the risk at the end provoked by geological hazards or terrain movements is related to the velocity. And, well, the velocity of the movement and the impact force of the moving mass. Here you can see a scale of different types of terrain movements that move at different velocities. And this is something that can be related also to the risk induced, because if the movement is slow, you can probably detect it in advance and evacuation would be possible. And maybe this is something dangerous for buildings, but not for people. But in the case that the movement is very fast, if people is exposed, it's very difficult to give alarm and to evacuate these people. So this is more dangerous at the end, or the risk is higher. So if we look at this scale, in the right part, so the most fast movements are landslides. So what's a landslide exactly? A landslide is a movement of a mass of rock, earth, or debris down a slope. The triggering factors can be very, very different. And here I would like to show you an example of a landslide triggered by rainfall. You can see the water infiltrating into the terrain. And suddenly, when this water has enough pressure to change the stresses, the failure is originated and the land breaks and goes down the slope. But other triggering factors can be also doing the same effect, which are earthquakes or the melting of the snow or permafrost, so they can provoke the same. So at the end, it's a matter of type of material and the morphology of the terrain and the presence of the triggering factor. Depending on these different actors, so that the type of material and the mechanism of movement, the landslides can be classified in very different types. This is a summary table of the British Geological Survey, but at the end it's mostly the same for every different institution. And here you can see, for example, a rock falling, which is this case, in this example, or earth, which is flowing, which is the other example in the left, which is an earth flow. So now going to the emergency field, I would like to just make a highlight on how different are landslides to the other two phenomenon of the project, which are forest fires and floods. Landslides, as I said, are very fast movements, which makes it very difficult for us to act during the response time, so when the event already started. So I think it's very important to have in mind that for the terrain movements and landslides, it's very difficult, it's very important to emphasize the preparedness. So we really have to work on how do we prepare before the event starts. So the big questions in this field of the preparedness are where, when, how big, how fast, how far, and how often do the landslides occur, and obviously if they are affecting people or objects or not. You can see here a picture of potential of landslides all over the world, and you can see that, well, landslides can occur almost everywhere, but it's not the same in all the parts of the world. So at the end, what we do, or scientists and practitioners do to assess the hazard is, well, actually the landslide hazard and risk assessment. The landslide hazard assessment tries to improve to learn about the occurrence of landslides in order to improve the planification of the urban settlements. So in places that we know that the landslides occur, it's better maybe to avoid construction, or in case it's not, it's compulsory to build, you have to take measures. And the risk assessment permits the risk mitigation. So if we know that there's risk, we really have to take actions to reduce it. And we can do it for preparedness, but also in the response time. And I would like to mention that only very few countries in Europe have laws regarding landslide hazard and risk assessment. So now I'm going to talk about the first step on the hazard assessment, which is the susceptibility, that tries to guess where and what type of process are going to occur in a specific region. So to delimitate the areas that are prone to landslides occurrence. What we normally do is we take the conditioning factors, which are slope, geology, land use, and some derived factors from these ones. We cross this information with historical information, so landslide inventories, and we can have, or we obtain a landslide susceptibility map, which says to us where is more likely to have landslides. But with this, we don't have the information on when are they going to occur. So we go to the hazard assessment. Hazard tries to say which is the probability of occurrence, and we obtain this information from the frequency of the events. So normally we look at historical series of landslides that we have from observations, records, or datation techniques. However, these ones are normally not complete, or they are too short, depending on the country normally. So a typical assumption that we do is that we think that if we know the triggering factor, which is the rainfall most of the cases, we assume that the frequency of landslides is the same as the frequency of the triggering events. Then by obtaining the probability of occurrence of a certain rainfall, we know which is the probability of occurrence of the landslide. However, there are many questions around this fact, and I think one of the relevant ones is that, is it going to be the same in the future? Because we know that now we are facing a climate change, and probably this is not going to be like this. Then with this information, we cross the probability of occurrence, so the frequency and the intensity of the hazard, and we have the hazard matrix, and we can delineate areas with different hazard or in the maps. So we can say here the hazard is high, so probably it's better not to build anything. But then in other areas it's lower, so it's okay to have it into account, but we can build there. And then for the risk mitigation, as I said, there are two main actions. One is the preparedness action, so mitigate the risk before the event starts, and the other is the response. So once the event starts, what do we do? To mitigate for preparedness, we try to reduce the exposure. So in this case, to protect the elements at risk you can see here rockfall nets that are protecting the train to be hit by a rockfall, or reduce the hazard. In this case, it's something similar, so nets, but these ones are trying to keep the material up in the initiation area, so this material is not reaching the lower part, and then it's less intense, the hazard. And then finally, so the mitigation action, the risk mitigation can be done with early warning systems or alarm systems. Here, I'm going to start with explaining what are the early warning and alarm systems. In this case, they are based in monitoring systems that can be in situ, so in the place where the landslide is going to occur, or remote. And specifically in this project, we are going to use both systems. Depending on the target that we are monitoring, so directly the movement or the triggering factors, we have different systems, and we can get warnings or alarms. So basically it works like this. When we forecast a critical situation, we can spread a warning, an early warning. Then when this situation is already measured, we can spread or alarm or a warning depending on how soon is it going to, the terrain movement is going to occur. Then once we detect the terrain movement and we have the event already, depending on the velocity, we can spread an alarm or a warning. And I think this scheme summarizes quite well what we are trying or we are going to do in the HEIMDALL project together with the CTTC. We are going to use satellite observation and interferometry to do so. So we are going to use basically satellite radar images taken in different moments with Sentinel-1, and using interferometry we are able to identify the deformation velocity of the land, and we can identify in a regional area where the land is moving. Another system that we are using are the in situ sensors, which can be installed inside the land. So, for example, we can measure the pore water pressure in lower layers of the soil, which is not directly the movement, but it gives us clues on the resistance of the land. And also we can measure directly the movement by placing crack meters, which are measuring the aperture of the joints in the terrain. And with this information, we can set some thresholds, and once these thresholds are exceeded, we can have the information that something is happening. Another system that we are using is the in situ sensors, the GVSAR, sorry. The GVSAR is a terrestrial ground-based radar, which is working well, similarly to the satellite radar, but in this case, the acquisition time is faster, so we have very frequent data. And by comparing the different interferometers, we can have the information on the deformation of the surface. And finally, I would like to present you a success story, which is, well, it's not in our area, but it's in Switzerland. This is a landslide in Preonzo village, which occurred in 2012. This village is placed below a slope which is known to be unstable, and it has been monitored by during many years. But in 2012, the crack meters installed in the area detected some movement that was going faster. And due to this, they installed in situ radar to measure continuously the movement of the land. Suddenly, some days before the 15th of May of 2012, there was an acceleration trend of the movement in the area, and the authorities, looking at this data that says that after some rainfalls, the movement was around 3 millimeters per hour or 4 millimeters per hour, they decided to close the road. And successfully, this road was closed before the big event happened with 300,000 cubic meters that collapsed in the area. And you can see here a picture of the upper part where there's a big joint in the upper part. And well, after this big event, they waited until everything was stabilized, so there was no risk anymore, and they reopened the road and everything was fine. So I think this is a good success story, and a good example to understand what we are trying to do. So just to summarize, well, terrain movements are an increasing risk due to the growing human development in the exposed areas. The risk depends on the velocity of the phenomenon, being the landslides the most dangerous ones. There are many types of landslides depending on the type of material and the movement mechanism. We can provide within the HEIMDALL project major contributions on the preparedness phase of the landslide risk management. A good knowledge of the hazard is required, obviously. And finally, the early warning and alarm systems, we have seen that they are a useful tool for risk reaction before and during the events. So, well, thanks for the attention. And if you have questions, I'm here to hear you. Thank you.